My name is Tejumade Afonja. Today we are going to talk about nonlinear modeling, cross-validation, regularization, generalization, kernels, things like that. And why do we care about it? Life is not linear. Usually there are ups and downs, so you need like to fit ups and downs kind of curves, if that makes sense to you. Okay, so my hope for today is that the class is interactive, and I have quite a number of slides. We'll see how it goes, but we will not sacrifice discussion for completion, if that makes sense. So we need to kind of like talk a little bit, think about it a little bit. Why are we doing what we are doing? And come back to the equation. I have a number of equations on my slides as well, but I don't want you to be overwhelmed by it. It's meant to explain something. And if you're not clear on that, you should ask questions and we can all learn together, think about it together. Some things look like it's trivial, but it's non-trivial to beginners, especially like when you're just seeing it for the first time. So if you encounter such things, I would really encourage you to just ask, just raise it, and we can spend a little more time understanding it. So whenever I ask a question, I encourage you to maybe raise your hand and unmute yourself or something like that, just to make the class go a little bit smoothly. And I'll keep my eyes glued on the chat as well. We can move into today's topic, and roughly we will cover all of these items. We'll start with some example motivation for nonlinear problems. We start with linear problems, then we slowly move our way to nonlinear. We talk about how to use polynomial features to make the problem that is nonlinear solved in a linear way. We also talk about overfitting, a natural problem that starts to occur once you start to fit many high order polynomials. And then how do we regularize this to make it generalized better? And we move into nonlinear, generalized nonlinear features and kernels and other kind of machine learning models. That's why we wrap up. And then I have some musings at the end, just like chatting about things that I thought may be interesting. If there is time, we can go over them. So example motivation. I have a question for you. What kind of model would fit this data the best? What do you think? This is an interesting data. It looks like this, and we want to come up with a model, a function, something that help us to approximate this data in such a way that we can just throw away this data and use that model to predict on new examples. Did anyone know? Nobody. Okay. Maybe we just fit a linear model, right? This is what we know so far. This is what we did a couple of weeks back. But well, if we fitted a linear model on this, is this the best fit to you? To me, it doesn't look great. Like there is one linear, like all of this point here would have a high error to the line that we fitted here. So definitely we can do better. as you can already tell, I'm trying to build up anticipation for other kinds of lines, the ones that are squiggly. So instead of trying to have a straight line, we can have a curve, right? We can even do much better than this depending on your data, but like this is a nonlinear model, and would you agree that this is better than this, in your opinion? It is better. Amazing. All right. So how can we, in nonlinear, exactly. So how can we find the best model that fit our data? All right. This is usually the question. And to do that, we would come from the linear model part, which we have seen a lot of in the past weeks. Week 8, we talked about linear regression, the linear relationship, where we have the line of best fit, which is the y equals to mx plus c. In your machine learning career, you cannot get rid of this. It's like the building block. You have to always remember it. So we always talk about it, the linear equation, because from there we can build up to multiple lines fitting and so on. And also in linear classification, it was the same idea, but applied to classification. I hope you can remember. If not, we'll talk about it. But to motivate these nonlinear problems, I thought maybe we'll look at real life data. And I was looking for something local. I found this Chicago Nigerian music Spotify dataset. So explore the dataset to find any of the features that looks nonlinear so that we can use that to build up the iteration. So it's not very, like, I found some. I don't want to spoil the entire talk, but let's keep going. So the Chicago Nigeria data set is a very simple data set. It shows you for each of the row is the track, the name of the song, and then you can find like the album where the song appeared, the name of the artist, whether or not the top genre of the artist when the song was released, the length of the audio length. Oh no, yeah, I mean how long the song is. This is in milliseconds, by the way. How popular the song is, whether or not it's danceable, and so on. You can find all of this information in the Spotify web API if you're curious. So when you go there, you'll see that there is a very nice one in which I saw a bit late after settled on the data set and prepared the lab. I found out that Spotify had a policy that you may not use this content to train machine learning or AI model. But they mentioned if you can use it for educational purpose or anything, this was it. So I don't know if this is allowed. I got this data set from Kaggle, not from the Spotify API, but yeah, I should look more into this, but yeah, let's proceed with caution. I'm serious in this data set, but I'm just telling you that this may not be allowed. Some of us have devoted already, so I don't have money, and you don't want to get into a lawsuit. Okay, having said this, so we will start with one feature, and one target. If you look at this, what do you think would be the right target? I mean, there's a lot of things you can do with this data set, right? And they don't provide you anything about like what it's used for. You can we just throw a bunch of features. But when you're trying to throw features, what usually are you trying to do? Like, I mean, if you think of Spotify data set, this kind of data set that I'm showing, what is a suitable task for this kind of data set? What would you say is a suitable task? Maybe to give each of the track, how danceable is it? I mean, that could be a target. Guys, I need ideas. What do you think? To suggest music, yeah, recommendation, exactly. Like what kind of, depending on what you're interested in. But then for this, let's not go like general. Like this is all you have, all of these columns. What kind of task can you do? What do you think? How popularity, the rating of the music. We don't have rating, but maybe you mean popularity, right? I don't know, because we don't have any rating column here, right? But yeah, it's very natural. Like when on Cargo, the person that put this data set there was trying to look at how popular this is, which is interesting, right? Given the track, can you predict whether or not it is popular? The higher, the better. So this is a regression task. Yeah, you can also predict the genre, right? Relationship between acousticness and popularity. Oh, yeah, that's true. Yeah, well, I explored all of this relationship, trying to find which of these features have some correlation with popularity. Not a lot of, I did not get anywhere. Like this, it just seems so random. And in the lab, you would look at the plot. Anyway. I thought that to make it easier to convey the concept of nonlinearity and not get too deep into the data set itself, I was looking at two features that I know that there would be some relationship. Can anyone guess that those features? Like, there's no way you can do it. By the definition, there is always a relationship between the two features. Maybe it's not too obvious to guess. Sound quality, how frequently the music is downloaded. Yeah, those are very nice suggestions. I'm just reading the chat. Okay. So these two features are the energy and the loudness, and genre and danceability. Yeah, there is some relationship between genre and danceability, maybe, but sometimes it's just like this values you have like a high, like is it like when you have very strong very fast music, people can dance more, but I mean when you have like slow music as well, you can also dance like then I don't know. How do you quantify danceability? Anyway, we don't have to talk so much, but I thought when I was looking at it, energy and loudness to me seems sensible. When something have high energy, it's loud, right? Even in the definition that Spotify gave, like in the description, they said energy represents a perceptual measure of intensity and activity. Tracks with high energy feel fast and loud. Okay, so I know that as you increase energy, loud increase. So I thought this is a good relationship. And when I looked at I looked at the plot, it actually looks like there is some relationship between these two. So our task for this talk would be trying to predict the loudness score given the energy level. May not make a lot of sense. We're just trying to, do something here to motivate and understand the concepts. So like, I'm not sure why you would, in real life situation, you have a Spotify data set and all you're trying to predict is the loudness given the energy. So may not make a lot of sense. But let's say in that world, this is what we're doing. Okay, so this is the 2D plot. Our x-axis, which is our feature, what we are using to predict our target, is called energy. So on the x-axis, we have energy, which is the feature again, and on the y-axis is the loudness, which is the target. What kind of task is this? What kind of machine learning task is this? Does anyone know? I want to predict loudness given energy. What kind of machine learning task is this? Because we need to know the task so that we can know what to do, like what kind of model to use. Thank you, Damlola. This is a regression task. It is continuous value. So does it look linear to you? What do you think? Does it look linear? Can we use linear regression? I mean, this is currently, this is our hammer. We just keep using it, hitting it, everything. It's like linear regression. Can we fit a linear model on this? What do you think, guys? Nope. Sarah said no, we cannot. Okay, so Sarah, what do you mean no? Can you please let me know? If you want to talk or if you want to chat or something. Looks feasible. Yeah, I'd say so. But if Sarah said no, we need to understand why Sarah doesn't feel like this is linear. There are many dense values to Rosetta. There you go, girl. Yes, right. I mean, the thing keeps going up and then at some point it went down and then it went up. It's like, looks linear, but also feels like it's not continuously, I mean, depending on how you look at it. I'm like, again, we are machine learning like practitioners here. We have the data. We want to figure out what to do with this data. We know something about machine learning. We know that it's a regression task. We have a bunch of models we could consider, but right now we only know about linear regression. So whatever, we're just going to fit linear regression on it. Okay, so we fit a linear model on it and we have this solution. This is the best we can do given the linear model. Some terminologies here now. So what have we done? Like when we say we are fitting linear model, what I'm just saying is that what we mean is that we have some y equals to mx plus b, which is line of best fit, right? And we can rewrite that as theta transpose x. This is important because you'll start to see notation, and I wanted you to map what that notation means so that we can always go back. Again, y here is our target vector and it's the loudness in this example. X is our feature vector. Right now we're considering one feature, but usually you would have multiple features. So it's a matrix usually, but right now it's a vector, and it's the energy. And the theta is the parameter of the model. This is what we want to learn. So the parameter of this line that we just fit now is what made the line look like that. It has a bias term of -13 or something. If you look towards the y-axis, and then the weight is some value that I need to do some math to deduce the exact number. So what we are always looking for is that we want to find the best or the optimal parameter or weight, something like that. So you can see I'm starting to use like different notation for different things, right? Okay, notation nightmare. So let's start. Let me introduce it to you. M is the same thing as W, is the same thing as theta, and they're all called parameter or weight. So we use that interchangeably. I'm sorry, it's just 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 letting you know, at least you know now. C is B is theta 0. So when we say y equals to mx plus b, it's the same thing as y equals to mx plus c, wx plus b, theta 1, x1, x2, if you have like multiple features, or in a compact form, which is like theta transpose x. So where theta transpose, or like just the theta without any subscript, would be you just putting all of your parameters into one vector, and then the last one would usually be your bias term, which is this theta 0 or theta or b or c or whatever you're comfortable with. I already said that parameters are also known as weights. Bias sometimes can be known as intercept. So in some literature, you would see intercept, it means bias. You see parameters, it means weights. It's just madness, I know. But yeah, just so you know. Okay, let's come back to it. So how did we find the optimal parameter for this line? Can anyone remember? We did this like 3 weeks ago when we did linear regression. Alan talked about how to find the optimal parameter. What amazing, Gamelia. Look at that, gassing me up. You remember? This is good. So gradient descent, right? We talked about we need to do dy dx, like we find the gradient and we continuously move towards the negative gradients because we want to keep going down. So we want to reduce our error. So we always like optimize the loss function, and then at some point we'll get to like a point where we cannot improve anymore. So then this would be our optimal parameter. But this is fancy, gradient descent for linear regression. Wow, it's like, look at that, amazing. This is a general optimization procedure, but linear regression is even more simple than that. Like, it does not stress out too much. You don't need to do gradient descent. It's nice to know, but you don't need it in linear regression because there's an exact solution for this. You can just write it out mathematically. So the optimal parameter can be gotten by just you find the correlation in your metrics, and like correlation terms is just like, it's this x transpose x, that would be like the correlation in your data. Then you find the inverse of it, x transpose y, and then you find the optimal parameter. But of course, you have to tread carefully here because there's a bunch of assumptions. It assumes that your data set is you don't have what's the word I'm looking for? It's full rank. A full rank meaning that you cannot. There's no correlation. It's independent. Yeah, the independent assumption. And then so once you have that full rank, you're able to like compute the inverse nicely. So, but if you don't have the full rank, it's you cannot compute the inverse. But there are other things you can consider, which like as you go into this, like you'll find it out. It's called pseudo inverse. So I don't want to go too much into the math, but I want to say it so that you know that like it's like building knowledge. You hear it for the first time, you don't register it, then you read something and you're, oh, So I just talked about pseudo inverse. Okay. What is this problem about least square? So it's like just adding to your knowledge base slowly. Okay. So we can look at how this exact solution, how did we come to this theta? And it's very, very simple. So it's just like go through it like very quickly, high level, not too much. Don't get too tired. We're just getting started. But this is important. You want, like, as you get into this field, you need to start getting comfortable seeing equations and trying to understand what it means. So we will start with the squared error term, which it was introduced to us in previous class, the mean squared error. So once you have the mean squared error, it just computes the difference, right, between your prediction and your target. And your prediction here is the x theta that we have here. And then, you sum everything up, you mean it. But we wouldn't use the mean version in this deep dive. We'll just look at the squared error term, which means that you're not dividing by the entire thing. And once you have the squared error, which is the E of theta here, and you differentiate it, we won't go through it. You drop the 2 down, you expand things, basic gradients, if you remember. If not, you can quickly look up how to do it. Then you set it to 0, then you move terms around and you get the optimal theta. So this is it. Like, it's not just like a few lines of code and then you get to the end thing, but it's nice to know how this thing is done. I just wanted to quickly note that. Well, it's all right. If you have questions, happy to talk about it, but this is just for your knowledge. You can come back to it. So let's come back to this. So we use that mean squared error. We look like for this fit that we have, we computed the error, the mean squared error, right? We want to know how well this line has fitted our data. And then the error is about 2.82. I mean, it's not 0, but it's also not like very large. So seems okay, right? 2.82. But I mean, can we do better? Is there any possible room to do better? Maybe instead of fitting it like this, like we have, maybe we can go like this, something like, if that makes sense, maybe that would be better. I don't know. But yeah, we cannot just stop there. We need to try more things because we are practitioners. We keep looking at things. So this is now moving us into this other topic called nonlinear regression and polynomial fitting. All right, so let's look at nonlinear regression, right? So thus far, we have illustrated linear regression. We said it's like drawing a line through the data. Or Alan said it's like walking the straight line. Something about line that is straight. But this idea of linear regression is a very, very fundamental, interesting one. It can be limited in the sense that it does not allow you to go beyond lines. Like, it's always a straight line somewhere. But given the right tool, you can bend the line a little bit. Right? So you can, the way you can bend this line is through creation of nonlinear features. So to give it like a superpower, I should have like an emoji like superpower for this model. It's just like you create some nonlinear features of your input data, and that has an effect of changing the way the line would look. It's still linear in the formulation, but it's bends it a little bit. I'll show you what I mean. Okay, let's look at this. On the left side, you see our nice straight line. It can never go beyond. It's always going to be straight. This is the way it is. This is the nature. You cannot change it. It's always straight. On the right-hand side, we see some straight and some curve. You see, if you zoom in into a part of the quadratic function, which is y equals the x squared, you see that if you just look at the left side and a little bit of it, it's linear. But as you go down, it curves. And then you see another linear. So we are starting to like twist the line, join something else, essentially adding more degree of freedom, if we can use that word, like, connecting things. This is like this, and then you can move things around. And on the other one, you see another polynomial, like x cubed. We have quadratic. What is cubic? You have a cubic function there. So then it's like a little bit curvier than a quadratic function. And you can continue to build up those order. They're called polynomial, right? Polynomial order. You can go to like infinite polynomial. That's a lot. So quadratic, cubic, you had fourth and fifth, I don't know what they're called. You just keep going and until you're satisfied. So this is like, just visually, this is what we mean by nonlinear features, right? Which I hope that makes sense to you. So for our problem, remember we have energy, which is our feature. We want to predict loudness. So one way to do that, we just create a polynomial feature, right? I just said it. We do like a quadratic function, which is this energy squared. So instead of having just energy, which is one feature, like 1 point, now we square it. So we append that. So we have the energy and then the square of it. And we've not changed the hypothesis function. It's still linear in the parameter space, in the sense that we still have to do theta transpose x, or mx plus b, or wx plus c, whatever you know it as. We are still doing a linear transformation, but but now we have a non-linear input. So the input is no longer linear in terms of it's just not just x. Now it is x. We have x and x squared. This is what differentiated. And so when we do that, the plot looks something like this. You can see it's before. Remember, it was like just a straight line, but now it's curved a little bit. I hope you can see that. Can you see that? And you see that it's not the same as what we had before. Are you able to see it? So why stop there, right, Sarah? Sarah, like, you were not pleased with it anyway before when we talked about linear. It's like, why stop there? We can increase it. X cubed, cubic function. What do you think of this? Is this better than what we had before, like in the linear case? Guys, what do you think? It looks better, right? Like with an exclamation, like Sarah was like, yes, this is what I'm saying. Don't do it like that. What's the meaning of this? Like, just make it curl. Yes. Okay. But I mean, now that we know that we can make things better, we might as well continue. Fourth degree of polynomial doesn't look that different from the third, right? How about fifth one? Oh, 10th one. What do you think, guys? The line is closer. Okay. It's getting too fitted. I mean, nah, you don't want that. Slim fit. Okay. Things are starting to look a little bit different from what we had in mind. I mean, okay, yes, we said we want curve, but It's like wasabi. Like it's now like trying to like look at this line here. It's like very well fit. They're just like now going through each of them, trying to get everyone. Anyway, what is going on here, guys? It's a quiz. It's a time of reflection. What have we done wrong? Right? We found out that we could increase this thing, and then we have like a square and it looks nice, and we kept going. Now we have this shape that we cannot explain, like a 100-degree polynomial. What is going on? Noise. We're starting to fit the noise in the data. That's a good explanation, because it's definitely looks like it's trying to get as much data point as possible. We are overfitting. Wow. Thank you for paying attention, because yes, indeed, it turns out that by increasing the order of polynomial, we have run into a very nasty situation where we have overfitted to our training data. So let's talk about overfitting. What is overfitting? And what is the problem it brings to surface? So usually in machine learning, like we really don't care about minimizing the objective on the given data. Like I give you a data, the data that I gave you, I say like minimize it. What is the best possible minimization you can think about? Like y equals to mx plus c. Like if it's the training data that I still care about, what is the best thing I can do? What do you think? If all I care about is the training data and the best fit for the training data, what is the thing that makes the most sense to do? Well, I mean, I'll just tell, like in my mind, it's just have like a dictionary, a lookup table. When you find this data, this is the answer. You don't need to do any machine learning, just look it up, like put it in a database and look it up. This is your best fit. This is the best possible model you can have. But this is not what we care about. We don't care about the data that we've seen before. Like, you know, like who cares? We want to be able to make some prediction or like make a statement about something that we have not seen before. But we know that it's still in the same, comes from the same distribution. Like it's a new data, but like, I mean, they all come from, like, I mean, let's think of Nigeria. So you can, like, the same distribution would be like, we are all Nigerians, right? But we're different persons. Like some people are in the ASS de Lagos distribution. Some people are in the like other community distribution. Some people share community, you know, in different distributions. So now we don't want to just be able to predict well on the data that we know, but we want to go beyond that to be able to make inference on the data that we don't know about, we have not seen before. So the error in linear regression that we try to minimize is the mean squared error that we've talked about before. I mean, you can just write it, or like write is this minimization objective function as minimizing over the parameter space, which is the theta or weight. And then you have the loss function. The loss function in the linear regression model would be, like I said, the MSE, but in another model, the loss function would be different. Okay. So, okay, so coming back to this, what we, like I said, what we really care about is that we want to know how our function, the function that we have learned, we want to know how it will generalize the new example, but still within the same distribution. Remember I said, like, people that are in ASS de Lagos, you can think of them as one distribution, right? So in people in Nigeria, you can think of them as one distribution. People in Africa, this is another distribution, right? Depending on how it's like, just like a group of people, like you can think of it as a distribution, right? But then if you want to move to another group, it may be that what you've learned about this group may not transfer, or they may share some similarities. Like different African countries are different in their culture, they're diverse, but there are some similarities, some shared struggles that we can all understand, something like that. I digress. So the higher degree polynomial that we saw before, the one in that we fitted 100 degrees, it has exhibited overfitting, as many of you have rightly pointed out. So, but they actually have a very low loss on the training data. The training data, we will look at it in a moment. You would see that the loss kept going down, but this is not expected to do well on new data. And then we'll show that in a moment. So you see what we mean. But to just motivate this problem of overfitting, it's that as the model complexity increases, in this case, we had the complexity can be measured in terms of the degree of freedom, which is the polynomial degrees that we kept fitting. So as we increase it, we make the model more and more powerful. The training loss would go down, but the generalization loss at some point will start, as it's going down, it also would go down, but at some point it just changes trajectory, start to increase. We don't want this. We don't want this. We want to stop at the point whereby they are both going down. They are both friends, close together, going down. The moment they start to go up, we say, okay, yeah, okay, it's okay. It has to. We can stop now. So this is the overfitting problem. It's very common in machine learning. But before we proceed, we just talked about generalization loss. Well, how do we compute this? How do we compute the generalization loss? This is a question to you all to understand if you're following me. Mean squared error. But on what data do we compute this? You're right, because we are still in the linear regression problem. So we're going to look at the mean square error. But on which data? Should we do it on the training data? I don't know. The only thing we've talked about so far is on the new test data. Thank you. You're following. So because we just said doing it on the training data would not inform us of anything new. So we need to find some new data to test this function on the test data. We were talking about needing some test data to quantify our loss. We wanted to understand how well the model that we built is doing. So we thought we needed to have a test set. So we'll talk about the machine learning workflow very briefly. So usually have the training, you have the data set, which consists of some features and label if it's a supervised learning task, right? And then you can you need to set aside the training data and the test data. And this could be 70-30%. So you have a holdout cross validation. This is usually referred to as cross validation when you set aside some holdout set of validation set or test set, depending. It all means different things in different contexts. So For now, we will use old out test set, or it could be like 60-40 or 90-10. So it depends on how much data you have. And once you have that, you train your model, you learn with the training data, you have a learned model. And then you estimate the performance of your fitted model on the old out test set. Then you have the performance. And optionally, if you're working in real life setting, you may need to now retrain on the entire data. Right? Once you have the right parameter value on your learning algorithm, and then you retrain on the full set, and you have your model that is expected to even offer better performance, because now you have more data, right? The more data you have, the more you can learn from that data. This is the idea. Okay. But what if you don't have enough data? What do you do? What do you do usually? For those of us who are familiar with this process, if you don't have enough data, what should you do? Okay. Synthetic data. Oh, I like that. You generate synthetic data. I like that because this is what I do in my research. Synthesizing new data, learning from existing data. But okay, this is interesting. You can exclude them, cross-validate the data. Yes, Samuel, this is what I'm looking for in this particular context. So if you don't have enough data, usually what you do is something called k-fold cross-validation. There are different techniques. One of them is to do k-fold cross-validation. And very briefly, what this does is that you split your data set into some k-disjoint subsets, also known as folds. So you're going to train on all of the folds but one. That one that you kept would be what you test on, and you repeat it. You repeat the training k many times, holding out like at each time you hold out one fold for your testing. So this is very, very, very popular. A lot of people that work with machine learning, especially if you're doing it in the industry, like you have like a model deployed in the world, you do a lot of cross validation to make sure that you can have you make sure that your algorithms see all aspects of your data. Does that make sense to you? So this is a visually, if you wanted to do like 5, okay, Samuel, please go ahead.
Okay, please, I want to ask, is it conventional that you use only 5 fold cross, like you only do 5 fold cross? Because all what I've been seeing recently is 5, 5, 5, 5, 5, n equals to 5, n equals to 5. Is that this conventional that you use 5?
You you can use as many folds as your data, like your computation resources allow. I think it's just people just use 5-fold because 3 seems a bit too small. 10, you may not have enough computational power to train. So 5 allows for a reasonable estimate. So it's just convention on the one side, but also about how much computational power that you have available to you. This is what I think. But if you have more resources, I definitely encourage you to try more. more folds and see if the averaged error that you get is different, significantly different than if you had just used a 5-fold validation or even less, something like that. Okay, so visually, what this look like, I just what I explained in the previous slide. You can just visualize it like this. Each of the folds, you have one fold. You keep the orange one. Here it's called validation set. Some people can call it a holdout set. So I have a question for you though now. So say you're choosing amongst 10 different values of a polynomial degree. You know, we talked about polynomial degrees where we were fitting higher order polynomials like 100, and then we found that something overfits. But now let's say we have like 10 different polynomial polynomial variable that we want to choose. Like we want to cross validate amongst the 10 different value, and you're doing K 5-fold validation. How many times would you train your model? I see 5, 50. Okay. Well, Ipadiola is actually the correct one. You would have 50 models. So remember that each cross validation, like you have, if it was just one value, one hyperparameter, we'll come back to that term, just one hyperparameter, then you would have to train your model 5 times. But now you want to choose between like 10 different values, 1, 2, 3, up to 10. So for each of those values, you would have 5 models, multiplied by 10, you would have 50 models. So yeah, I hope that is clear. To those of us that think it's 5, is it clear? Yes, great. Okay, so there's another technique that we that you would also see being used, maybe not as common as the K-fold, again, due to computational reasons. It's called the leave one out cross validation. You can think of this as the natural extreme for K-fold, when your K equals to the number of training example that you have. What does that mean? So at every point, at every like time you want to train your learning algorithm, you train with all of your sample but one. So you validate. Once you train with every sample, the one that you left aside, you test on that one sample, and then you do it again, test on the other sample, and you do this m times, right? Always testing on just one example at every time. And this is actually very, very, the average error that you get goes very low. So leave one out is very effective, especially when you have very small sample set, where you cannot afford to just leave out 70-30%, like that we talked about in the canonical cross validation, or like 90-10 or like 60-40, name it. So you just cannot set aside any part of your training data, and you still want to be able to learn and to validate and to be able to estimate your error, how well your model generalized. So you can do this, leave one out or K-fold cross validation. Is this clear to you? This idea of leave one out cross validation? Yes, thank you. So I have another quiz for you. Consider you have a data set that has 10 samples. If we employ the leave one out strategies, how many models will be trained? I already said 10.
If you want to use the cross-validation method, the K-fold, you separate the data into 9 different places. One is be separated. That means you are training 9 at a time. The one that is like 1-fold, 2-fold, 3-fold, 10, 10. if you are going to you employ the leave one out strategy, which is most likely like the careful. I don't know. That's what I think.
Yeah. Okay. How about the camp that think it's 9 models? I will try. Does anyone want to say why they think it's 9 models? N-1? Okay. So we don't spend too much time on this. It's going to be 10 models, right? Because at every time you have 10 samples, you train with 9 samples, you validate with 1 sample, you do that again, the next 9 samples validated, and you have to do that 10 different times because it's like the K-fold. You go through them, every sample needs to be in the data set at some point. If it's not a test set, then it's a training set. So you have to go through them one by one, and you have 10 samples. So you would end up having 10 models. Is that clear? So it's a combination, like, I mean, if you want to phrase it in that way, in a much more compact form. Thank you for bringing that up. Is that clear to everyone? If it was the K validation, it's like would be like 10 choose 5. Is that it? Anyway, don't let us spend too much time on this. But there are also other variants, right? Like this stratified cross validation, where you try to keep approximately equal percentage of the positive and negative examples. And there's a warning here that K-fold is not always better, especially when you have a time series prediction. This is all trying to help us understand like the machine learning flow. But usually you just don't have like a train and your test. You're experimenting, you're changing things. Like we just talked about how you have polynomial degree 1, 2, 3, 10. Those are parameters, hyperparameters that you change every time and you get a different result. And so you need to be able to learn this hyperparameter. This is, and then using this idea of cross-validation can help you test many different parameters. So I'll quickly skip through this, where the flow that you have so that we can move on. But this is a quick question. So can we use the test data method for hyperparameter tuning? What do you think? Very quick one, so that we can proceed with the slide. Can we use the test data? Like you have just the test data that you hold out. Can we use it for hyperparameter tuning? No. Okay. No, you can't. Why? Why can't you? Why can't you do that? Okay. Maybe this is very trivial. We all know that. We've always heard that you shouldn't use your test data.
Yeah, I wanted to say like the hyperparameter tuning, like it has to do with like the training data set. So you do tuning with your training data set, so it will not use. I don't think you're using test data set to tune your model.
Well, so the thing is that you need a data set to tell you how your trained model is behaving. So you train your model, you use one data to compute something like a score for how that now represents how well your trained data has performed. And then you can do that for multiple times. But the problem with using a test data to do that is that you can now start changing your hyperparameter, which is usually what you do because you're trying to make it better. And you can no longer use this test data to compute the generalization law, because then you'll be overly optimistic about the results. You've seen it multiple times. You've learned in the process of using it to compute the loss, you're learning something, you're gaining some additional knowledge. And this is not the point for a test data. It should be something that you set aside that you never touch until you have everything in place and you just want to say, oh, okay, how well am I doing? So if you ever use your test data for hyperparameter tuning, you just have to throw it away and go to get new test data, right? Hyperparameter, I mentioned that earlier, is just something that you use. It affects your classifier. You use it to make your model better and things like that. So I don't want to go too much into this because we don't have a lot of time anymore. So we can move on. And just like Bala just said in the chat, we instead of doing like a two-way split, which is train and test, we can do like a three-way split if you have enough data. So you would have train data, validation data, and the test data. And test data, you keep it separate. Validation data, you use it to tune your hyperparameter. I hope this is clear. But in this, for the remainder of this presentation, we'll come back to our setting, which is just training, just having two different sets, the training set and the ODOT test set. Okay, should we take this quiz? I'll give you as a way to think about it, the difference between model parameter and hyperparameters. So that was a very short segue to train test set because we wanted to measure the generalization error using some old out sets. So don't let us forget where we were. We had this polynomial feature, which was 100, and it started to overfit. So now we have set aside some train data and also test data. And you can see that roughly they're still in the same distribution. The test data are the one that are marked in orange. And what we will train with at the data is the data set that is marked in blue. The next thing we'll do now is that we train different polynomial degree from we had 1 to up to 100. And we just measure the error, mean squared error loss for each of them. And what is shown here? What can you see? What can you observe? What can you observe from this plot? It looks like the training set, the error for the training set is decreasing or decreased almost at 0. And the error for the old out set or test set at some point decreased and they started to go up. Can you see that? Let's zoom in a little bit. Can we zoom in a little bit? Okay, this was a question, but we'll come back to it later. What is this spiking thing going on in training error? So zooming in a little bit, we just reduce it to maybe polynomial degree of 4 so we can see the loss trajectory. At some point, we had the test error go down and then it went up at about polynomial degree of, at 2, it went up, but 1, it was good. And polynomial degree of 1 is what? It's the linear curve. So my question here is that why is the test loss increasing? Does anyone know why the test loss is increasing? Yeah, someone said the curve is overfitted. So this is for this question, it would be because at some point, as we start to increase the complexity in our model, remember we talked about model complexity, the training error will keep going down by definition. It will always go down. You always reduce the error in the training set, but the old out sets start to increase because you're having a complex model that does not generalize to the new unseen data, which is the point we're trying to make. So the variance is in, Dolamu said the variance is increasing because it doesn't perform well on newly tested data. Yes, this is correct. So how can we make it perform well on test data? In order to perform well on test data, we can do something called regularization. And we quickly motivate that. So coming back to this, how can we make it generalize better? We can make sure to reduce the complexity. So regularization here, it helps us to make sure that, Dalam said reduce the weight here. So this is what we are going to do. We are going to control the model complexity by making the weight smaller. So we want to, like, we don't appreciate very large weight because it makes our model complex. Regularization term would add a penalty that makes the weight of our data or the parameter, it will make them smaller. To go into depth a little bit about it, the formalization for a regularized least square, it looks exactly like the least square, the unregularized one, but now we've just added an additional term called lambda, which is the regularization parameter that helps us to penalize the model when it has a very large weight. So we want the model to always prefer simpler solution. And so I want you to think about what happens as the regularization parameter gets really big, like 1,000 or something, or when it is 0. Just think about that as you look at this formulation. So what this formalization is doing is that it's going to trade off the loss of the training sets with this penalty value, and we vary from lambda equals to 0, which would be like unregularized version, which is what I told you to think about in the previous slide, to lambda equals to infinity, which would be like we are very, very like strict about the complexity. So essentially, eventually when you get to infinity, you just end up with the bias term. There's nothing more. You just kept like every like all of your weight will just turn to 0 or something like that, and what is left is just the bias term, if you can think about that in that way. So given that equation that I just showed, we are going to apply it on this data set. We want to reduce this complexity to make it fit less, like not like overfit. And once we apply that, the weight before was very large. You can see minus 6.4 up to times 10 raised to the power 7. This is order of magnitude of like 6 million, 60 million or something like that. This is a lot, like negative 60 million. This is very huge. So the moment we penalize it with a lambda equals to 1, which is the regularization parameter, you can see that like we went from this wiggly curve that overfits to a simpler model, which kind of like look like our square quadratic function a little bit, not exactly quadratic. But what is nice about this is that now you have a very small weight. You can see that or like most of the weight in the first couple of like the first few parameter has been set to like almost 0. So we went from over like negative 60 million or something to now like almost 0. So it has tried to reduce the weight of all of this model. So to visualize this, the degree of coefficient, which is this regular a degree of coefficient is the polynomial term, sorry, like from 1 to 100. On the left side, left plot is the, like when we have not regularized our model, we see that as we increase the complexity of the model, the coefficient weight starts to increase. But for the regularized version, as we increase this coefficient, it starts to decrease with lambda, like let's say with lambda equals to 1. So if we just regularize it, like choosing lambda equals to 1, we'll see that like as we increase it, then we start to have very low weight. Okay. Here I also show that this is the effect that you find on your training/holdout set, whereby the average on the y-axis we have the average squared loss, and on the x-axis we have the regularized parameter that we've been talking about. And as you increase the regularization parameter, you see that you start to have better generalization between the training distribution and the holdout distribution. But as you decrease your penalty, you start becoming more and more lenient, and then also the complexity increases, and you can see that the generalization gap between your training set and your holdout set increases. So this regularization is very powerful. When you're training a model, you usually, like if you're using like a least square regression, for example, you always use the regularized least square, which is also known as the Ridge regression if you're using L2 regularization. But if you're using L1 regularization, this is called lasso. So you may have heard about these terms. Okay. I'm going to skip this, but I will share the slides. Then you can go into how this regularized least square is derived. It also has an exact solution, like the unregularized one. That also, so you can just go over it. So this is the last segment. For the next 15-ish minutes, we'll just quickly go over some general nonlinear features. So we are aware of other ways of creating these nonlinear features. So far, we've been talking extensively about polynomial features, but we can also use something called RBF, radial basis functions, and generally just a little bit of details about kernels, but not go into depth because these topics deserve a class of their own. They're very, like the mathematical intuition, it's quite different. So more general features, if we wanted to move from a single raw input, let's say we have two features now. We're no longer dealing in one dimensional feature. Now we have two features like x1 and x2. If we wanted to transform these two features into, like using the polynomial features, it's not just going to be x1 squared alone anymore, right? So we would have x1 squared, x2 x2 squared. Then we would have the relationship between x1 and x2. All of this now, instead of having just like 4 features, which would be like x1 squared, x2 squared, x1, x2, we would have 5 because of this interaction between x1 and x2. And the 1 is just the bias term, like whenever you see 1 in that kind of vector, it's usually just because of the compact notation of the multiplication, so it's okay. So what does this, this is just telling you now that we have like a multivariate polynomial features, and this is usually how we would like define them explicitly. So whenever you see someone do a polynomial degree 2 on 2 features, you're expecting this number of features to be generated. So just to show you with real numbers, let's say you have x1, x2 features, and it's like 3, 2, 16, 3, 1, 1, and so on. When you transform this is transformation into a polynomial space of degree 2 that we talked about. It becomes something like this, you just have like 3 squared, and then 3, and then 4, 2 times 2, 4, and then 2, and then 3 times 2, 6, and 1, so on. So this is important to keep in mind, because eventually we'll move on from explicitly doing this calculation to a space where we don't have to do this explicitly. But in the it does this implicitly, but the idea is still the same. This is what it's trying to do. Like, it's trying to do a lot of combination of your input space. Samuel, you have raised your hand. Do you have a question?
Yeah, please. I really don't understand this computation going on here. The x1, x square, x superscript 1. I don't really understand what's going on.
Okay, thank you for the question. Remember that before we've been dealing with one feature. Let's say x1.
Yeah.
And that one feature, when we said that we can have a polynomial feature of degree 2, we said that would be x squared, right?
Yeah.
So that would be like you have x1 and x squared.
Yeah.
So so we are no longer just in one feature space now. Now we have 2 features. Okay. Like in your data set, you have 2 features. And we still want to do polynomial of degree 2, right? Like, can you tell me what you think that would be?
Okay, now we have 2 features, x1 and x2. Am I right?
Yes.
Okay.
So we will still keep the x1 and x2, but we want to augment it, right? The whole idea is that we want more features, with polynomial degree. So maybe we'll do x1 squared as well, right? That we did before. And then we can do x2 squared for the second feature.
Okay, this theta 2 that has 3, like this other column by the right hand that has theta 2, under it theta superscript 1, it has 3. I don't know, and x2 here on this other x2 features is 2.
So like the subscript is just telling you that for the first training example.
Yes.
It's not the multiplication thing going on. It's just it's notation. Sorry, when I talked about notation nightmare. So the subscript is just like training example 1, training example 2, up to training example M. Do you understand? It's like your first example, the second example, your third example. This is not the multiplication that is going on. Yeah.
Okay. Because like at the top here, where these vectors have been lifted, I can see that the x2 x square subscript 1. I understand now. I guess it better.
You understand now, okay?
Yeah.
So now you have x2 square, and then you now need to also account for the interaction between x1 and x2. So you just multiply both together as well.
Yeah.
This would be like your 5, 5. On the right column where you have 5, 5. So for the concrete example, you have x1 for the first training example is 3, x2 for the second training for the first training example is also 2.
You have 16.
Exactly. So you have 3 squared, which is 9. Then you have 3, which is the second one, and then you have 2 squared, which is 4. Then you have 2. Then you have 3 times 2, which is 6. Then you just carry over the 1.
Okay, I understand now.
Does that make sense?
Yeah.
Is it clear to everyone? Thank you for asking. I think this is, it's, I mean, yeah, for the first time, it seems intimidating, but it's really like just algebra. So this idea is really like, it's really, intuition is really important, because this is like the fundamental thing that kernels do, which I briefly introduced. Like I said, kernels deserve like a class of its own, or even multiple classes of its own. It's a big topic, but the general idea here is that it's a general framework that can be used to generate like features that we call general features. So the polynomial features that we've been talking about can be formalized in a way that you can have any degree of polynomial, and you're still able to like to implicitly learn it, or even make it explicit. So so kernels would implicitly help you represent some I-dimensional feature without you needing to like write them out one by one. The way we're doing x1 squared, x2 squared, x1, x2, you don't need to write them out but this is what it's doing implicitly. And just a cartoon representation like would be like, usually when you hear about kernels, it's like you have this non-linear data, very non-linear. There is no kind of linear like a straight line that you can fit on this left data. It's just not, you just cannot fit any straight line anywhere. There's always error, because you have two classes. The red class is in the middle, and the and the green class is surrounding this red class. So the only way that you can do this is that you can be a little bit more like, think about it like, can we move this problem from this space of two-dimensional to another space that allows you to use a linear classifier, or like a decision surface, like an hyperplane, some line, which in 3D it's no longer a line, it becomes a surface. This is why it looks like a surface. So you can see that it's still the idea of linearity, but in 2D you cannot fit a linear model like a straight line there. But the moment you transform it to that three-dimensional, in this case, in this example, you're able to like fit a linear surface, and then your problem becomes solvable. It's a separable, so you can separate it in this dimension. So every time people talk about kernels, it's usually like this, trying to understand how to generate higher order features, and how to transform your problem to a space where it is easier to solve that problem. And this space does not have to be you can have infinite dimension. So it does not have to be in 3D or something. I know it's hard to visualize what infinite dimension means. So, but it's just like, just think about this as some space where everything is just solvable there. Of course, like that space have some rules that we're not talking about here, in terms of the behavior, the things that needs to be satisfied for you to be able to do these things in this space. But yeah, this is the general idea. Okay, so like, given the time that we have, I wanted to talk about radio basis function, but maybe we just just tell you that radio basis function is another kind of like feature representation way, where instead of having like polynomial feature, we can have like a set of Gaussian features or functions fitted on your data set. And this formula here is a Gaussian function. And so just if you want to think of a Gaussian function, it's usually this bell-shaped, right? The wider it is, the higher the deviation in it. and the mean is the center of the Gaussian. So here you have a mean of 10, and you can say that this Gaussian peaked at 10. So you can have a mean of 0, it will peak at 0, and so on. And this is exactly what Radial Basics uses. It uses like this idea of having this kind of functions to fit the data set. In multi-dimension, you can think of it in this way, in 3-dimension rather, would look something like this. So what we would do is to fit many of this Gaussian, like, so here we have 10 different Gaussian, and we just like, you just choose different kind of center and you fit it multiple times. And by doing so, you're able to to learn some sort of curve on your data. And so what is nice is that you can also combine these RBF functions as a linear term. So you still come back to your old idea of linear equation, which is mx plus b, wx plus c, or things like that. Everything ends up coming back into that format, like if you reformulate your problem well. And yeah, so like just to quickly conclude on this part, so linear RBF is very, very powerful. Usually when people are talking about non-linear functions and you're trying to fit non-linear data, one of the kernels you would consider is also RBF kernels. So you would see it come up. So I hope this gives you some intuition as to how like what it looks like when people fit an RBF kernel. And here we show 2 different plots. On the left side, you have RBF kernel, but all of the parameters have been set to 1, and so it looks like if you have summation of them, it looks like that. But on the right side, the parameters have different values, and you can see that you start to have a different kind of curve, right? So which is like what you're looking for, more degree of freedom, so to say, so that you can fit your data better. And using this idea of RBF kernel, you can also fit this data set that we've been working with in this way. You can see that you're able to have a fit that looks like the cubic one when we were doing polynomial feature, but maybe a little better, because you can see that some of these data point are fitted well. But why stop at 10 kernels, right? 10 you're using 10 RBF kernels now, like the Gaussian that you're fitting on it. You can fit 100. Well, then you come back to the problem that we had before. You start to overfit. Like, every time you just fit so much, this is not going to generalize well. So you can also regularize your RBF kernel. It's not as straightforward as the regularizing the least square regression, but you can do it. There's regularized version as well. And so yeah, this is all about the kernels and having generalized features. And one of the models that appreciates this idea of kernels the most is called support vector machine. We would not dare to go into depth on how SVM works. Just takes more time than this, but the whole idea is that you're trying to maximize the margin between the support vectors. So it's usually called the maximum margin classifier sometimes, even though people think of there is another term for maximum margin classifier, but this is the idea. You want to maximize the gap or the distance between the support vectors between your different classes. In this story example, you have your class green and your class blue, and your best hyperplane would be the one that have the widest margin between these two classes. So So yeah, a support vector machine, if you use like any kind of like sklearn, like the popular module for that has all of this machine learning algorithms, you would see that it has an hyperparameter called like a parameter of the function that has like kernels, and you can choose the kernel that you want to use. We'll see a little bit of that in the lab later today. So like we didn't cover everything, right? Like we didn't cover nonlinear classification. There should be more intuition on kernels, support vector machines, and so on. I really need to look at the slides. This was the format of my slide follows closely the CMU data science course given previously by Professor Cohort, but now by our community in the past as well. I encourage you to look at the slides and also the notes from this link by following this link. And yeah, we can also do much more. Instead of just using one feature to train the machine learning model, we can try to use all of the features, right? Multivariate. So you should think about extending that, but be cautious. I'll skip over the musings for now, but let's this is the end of my presentation.